this video, let me play it. This is a video posted on Veritasium's shorts of two falling ladders. The one on the left hits a table, the one on the right does not, and the one on the left ends up falling faster. You can see it in a second. There you go. So you notice that ladder B hitting the table ends up ahead of the other ladder. And so I think I understand how this works. I'm going to explain the idea in a second, but really you don't understand something fully until you model it. So I want to build a Python model, and I did, and I would normally do it live, but it was way more complicated than I thought. It wasn't complicated, it was just tedious. Okay, so let's switch over to paper and let me show you what's going on here. Okay, so here are just 3 rungs of the ladder, and they are tilted, and that is important. So when this thing falls with an acceleration of 9.8 meters per second squared before it hits the ground, everything's fine. And there's actually no tension between these strings. And here I have 4 strings. 3 ladders, 4 strings. Now, what happens when this hits the ground? Well, when this hits the ground, there's going to be a force pushing up right here, because of contact force with the ground. That is going to change the momentum of the stick, but also change the the angular momentum. It will exert a torque on the stick, and it'll cause the stick to rotate. Now, once the stick rotates, this distance becomes shorter, this distance becomes longer. So strings have an important property in that they can't push. So squishing this doesn't do anything, but stretching this does. So this pulls down and it pulls on this piece. So now this piece wants to rotate, but it's attached to these 2 pieces up here. So there's a downward force on this piece that's going to make it accelerate faster. And then this is going to pull on these 2 pieces and it's going to accelerate faster. So this collision causes it to this to rotate, which exerts a tension on this one, which pulls it faster. Now, once this end hits, no one cares, right? It does indeed exert a force on that, but there won't be it won't push up on this rung. You can't push up on this rung because it's attached by strings. And then when this one hits, it will pull down on that side, blah 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 blah, and that side. So if I want to model this in Python, and I already modeled just a stick hitting the ground, and I thought it was great and had a great time, and I'll link a video to that video down below. But now I have to model these things too. So every stick could have, let's actually pick this stick right here. I drew it wrong. Let's pick that stick. Let's draw all the forces acting on that stick. Well, I have the center of mass right there and have the gravitational force pulling it down. And then I also have these 2 tension strings right there. So I labeled this T3L and T3R. And my labeling convention is part of my problem, but it is what it is. I'm going to stick with it. So this is a force, that's a force. We have, and they could be 0 or they could be something. Okay, so the first thing is, how do I calculate the stretch? And so let's call this length SOS. It's the short, unstretched length. And then I can calculate this length, which I know this is out of control, I called this the vector S3LS. It's the short side on the left thing, okay? But it's the vector from this point to that point. And then I can calculate if this magnitude is greater than that, then there will be a force. So the tension would be equal to, on this, T3L, would be negative K string, it's a spring constant, times, actually positive. It's going to be positive, times, because I have L going down, I want to calculate the force on that. And that was my mistake. I made that mistake. It was kind of embarrassing. Took me literally a day to figure out. So then I have the magnitude of this, S3LS, magnitude minus SOS, which is just a scalar, times S3 SLC. There's my problem. S3LS hat, a unit vector. But this will give me the force. The more it stretched, the greater the force, and that's how springs work. So the more this pulls down, the greater the force. I just need to pick a value for the spring constant. I need to put a statement in there to say, okay, what if that is greater than this, there's a force, otherwise the force is 0. Okay. And then I do the same thing for this string. Now when I get to this stick, it has a downward tension and a downward tension possible on that side, but it also has this tension, right? If this pulls down on stick 3 to 1, then it pulls up on stick 1. So that's how I'm going to calculate all the forces. Down here, same thing, except it's going to be a upward pushing force if this gets below the floor. Okay. Now we have a couple things. If I model these as cylinders, which I did, I need to find the endpoint. So I'm going to call this center of mass R3. That's the vector center right there. So how do I find this? How do I find that? Well, I also have an angle theta 3. So if I know that, and this has a total length of r, so I can find this vector right there. This is going to be r over 2 times cosine vector, cosine theta 3, sine theta 3, 0. So once I know R3, I add this to it, and I get this end piece over there. And then I take the negative of that to get down to here. So I can find all these pieces, and it's important when I draw the cylinder, it starts with one point, and then we draw the axis to the other end. So it's a lot of stuff. And then I just let it fall, and that's it. Okay, let's look at my very, very, very sloppy code. I'll actually run it for you first, and then we can look at the code, and then maybe plot something new, just to add a little bit to it. Okay, computer, here we are. Okay, and I will give you the code. Is this big enough? Let's see, maybe a little bit bigger. Okay, it's messy. Okay, so right off the bat, I made a bunch of graphs. I made 5 graphs, and that's because I was trying to troubleshoot what was going on. And we're actually going to plot. I'm going to change this graph to plot the force on the top ladder, the y component of the force. It'll be fun. Okay, now I have G. That's the gravitational field. Just some constants. They all have the same mass, but I put them as different variables in case I want to change it. And then I actually have 3. No, I have 2 spring constants. I don't know why I put. Oh, I have 3. I have 3 spring constants. So this is the spring constant between the floor and the stick as it pushes down. K2 is the spring constant as it pushes back up. And that allows, can you see my little stick here? Once it pushes down, it compresses the spring, but when the spring pushes it back up, it's a different force. And that gives it an inelastic kind of collision, so it doesn't bounce back the same way. You can change that. You can put these back both at 500. You do what you do you. And this is the spring constant between the strings. So you can change that too and play around with it. That's that. These are the moments of inertia of the stick. So that's the moment of inertia of the stick rotated about its center mass, 1/12 mr squared. I thought about what would happen if you didn't have a moment of, if it was a different moment of inertia. Would it increase the moment of inertia, make it more or less likely to accelerate? I think decreasing the moment of inertia make it better, because then make that thing rotate more. I think it all washes out in the end, maybe. I don't know. LG is just the size for the ground. The ground, this is just a box, right? I'm drawing the ground. Starting off with my initial positions, the ground's at 0, so I'm at 0.4, 0.4, 0.4 higher, that's that. And then the angles are 25 degrees. 25, negative 25, 25, because they're tilted. This finds the endpoints, all those endpoints, right? So here you can see my terrible notation. And yes, I could have done this with a list and stuff like that. I didn't. So, and I think it's important to have ownership of your code. If it's something that you understand, it's not the most elegant, that's fine. So this is the position of stick 1 on the right, R1. R for position, capital R for right, and 1 for the 1 stick. And then so it's just the same, just what I said. There's the center position plus that vector. The left is that minus that vector, and so forth. And so I find all 6 endpoints of the 6. Now I'm going to make the sticks. Actually, yeah, that's fine. Here's stick 1. It's just a cylinder. I give it a momentum of 0 and an angular velocity of 0, right? It's not rotating. Omega is the angular velocity. Stick 2, same thing. Stick 3. And then I set the lengths of the space, but how long is a string? And so instead of setting the length of the string, I just take the difference between the points and say that's how long the string is. It's not stretched at all. And so I have SOS for the short end and SOL for the long. I did it again for the other strings because I thought maybe there was a problem, but this stuff you don't need. You don't need these 2 lines. I made, because there's 4 strings, they all had both of the short ones are the exact same length, so it doesn't really matter. This part right here is just the string, makes the strings as cylinders. Time, and I had a very, very small time step. I was trying to solve some problems. You probably don't need it that small, but smaller is better, so that's cool. And then run equals true. That was a troubleshooting thing, and I'll show you what I did to troubleshoot, because troubleshooting is important. T-stick is another stick. I said I was going to run it. So T-stick is a stick it's a free-falling stick. Let me run this, and you can see what it looks like. So it's not running in full speed. And that's the unattached, unhitting stick. So you can see it is, this is a little bit, if you look at the center mass, it's hard to tell, but definitely that end of it is lower than this end. So that's that T-stick. Okay, so now for the magic. So when we do a numerical calculation, we count for each object. We calculate the net force, we calculate the net torque. And then the net force changes the momentum. The net torque changes the angular momentum. And the gravity doesn't change the torque. Rate 1,000, that's fine. Calculate the gravitational force, that's a vector, that's fine. These right here are the force vectors between the bottom rung and the floor. So every time I get back to the loop, I set it equal to 0. So once it loses contact with the floor, it's 0. Okay, and the same thing's true right here. These are the tension and the strings are all set to 0. At the beginning of every loop, they're set to 0. Okay, and then if I have to have a force, I recalculate it. Here's where I calculate the force from the floor. So if the position of stick 1 on the right is lower than 0, 0 is the ground, then I can calculate that upwards pushing force. And then if it's rotating, I use the angular rotation to tell if it's moving away or towards the floor, which isn't actually correct. It could be rotating this way and moving away, but that's fine. I didn't change that. And here's the left stick, and then I start doing the same thing for the strings. So the first thing to do is to take that first string, the long 2 string, and I say, okay, what's the vector from one point to the other? And then I can say, is that greater than the unstretched length? And that's what this does right here. And then run equals false. That was just, I was having trouble figuring out which string was stretching first, so I put these stops in there. As soon as they got stretched, I stopped the loop, and I could see what was going on. That's for. And then this just calculates the force. It's exactly the equation I said, K times mag S2LS minus SOL times norm S2LS. Okay. Right here, I just do it for the next string. I thought the strings on the third one were blowing up, but they are all blowing up. And it's the same thing. I have 4 strings. I have 4 calculations. They're all the same. Now here I calculate the total force. So force on stick 1, it has gravity. It has the 2 forces from the ground that could be 0, maybe not, and then 2 tensions pulling up. So T2L and T2R are the forces pulling down on stick 2. So I have a negative sign because they're pulling up, like that, on stick 1. And then same thing for stick 2. It's got gravity, 2 downward tensions from stick 1, 2 upward tensions from stick 3, and so the up ones have a negative sign, and then stick 3 just has gravity and the 2 downward tensions. This is to calculate the torques, right? But in order to calculate the torque, I need the vector from the center to where that force is, and those forces are applied at the ends. So this RRR1, RRR1 is position R, right stick, And I don't know why I put another R in there. I just did RR, so I wouldn't confuse it with RR1, which I had already. See my bad naming convention. So it's just a vector from R1 right there, which is the center, and this is the location of it with respect to some external origin, but I need the vector from the center of the stick to the end, and that's what this does. Then I can calculate the torques, so that's just calculating the torques. Now I update the momentums of each stick, including my test stick right there, right? It's still going to fall. I calculate the angular acceleration. So I said the torque in the z direction, z is out of the screen, is equal to I times alpha. So I could calculate alpha with the angular acceleration. And then I can use that alpha to update the angular velocity for all of them. And then I update the position using the momentum. I update the angle using the theta and the omega. And then I just, what does this do? Recalculate, I recalculate the ends of the sticks, right? Because if the sticks move and rotate, then I need to know where those ends are. I need to know where those ends are so I can draw it. So I move the sticks to their new positions. I change the axis. And then I move the strings. I just recalculate where they should be. And that's it. And then this is just, I didn't plot. I'm going to show you the graph. I just plotted after 0.2 seconds. This is a plot of the right side position of stick 3 at the top versus the right side position of the test stick that doesn't not attach anything. And I'll show you what that looks like. And then I print out a whole bunch of stuff just because I was troubleshooting. So let's run this again. And then we will do something fun because I have to add something to it. So it's falling slow because I told it to go slow. And I stop because I didn't calculate a force between this stick and the floor and this stick and the floor. I should. I don't think it'd be too hard to add on there. But, and it wouldn't be too hard to add another stick up here. I just didn't do it, you know. And then so here is the right side of that top stick along with the falling stick. So you see they're falling together until about here and they start to separate. The table hitting stick has a lower position, so it increased in speed. I mean, it had a greater acceleration down than the other one did, and that shows the point right there. And then I did print out the difference in, I'm pointing at the screen, you can't see it, this position versus that position. So, okay, let's make a graph. Let's make a graph of the total y component of force on stick 3 as a function of time. That'll be fun. So the first thing we want to do is to go up here and edit. And I guess I should change this to force. F in newtons. Okay, and I'm going to do, let's just get rid of the label. I don't need that. And it's going to do F1. And then down here, so I already calculate, where did I do it? I calculated the force on 3. It's Fn3. I already add up all that stuff. So let's just plot that, Fn3.y. So I'm going to plot this. I'm going to get rid of this. I'm going to dedent this. And then I'm going to plot Fn3.y. Is that what I called it? I just saw it and I forgot. Fn in lowercase n. Fn3.y. And then I'm not going to plot this. Okay, let's see what that looks like. Oh, and it's going to do it from the beginning. So you'll notice this little squiggly stuff here. That's kind of cool, right? So that's kind of cool because it shows that when I move one thing and then move the other, they can get off by a little bit. And so there can be a force pulling them together. But it's super tiny. You can't even see it in this case. Now over here, you'll notice that it never has a positive force on it. It never does. So -1. Oh, because it had a mass of 0.1. So the 0.1 times 9.8 is -1. And then it decreases in force down here, which causes it to speed up. So definitely the momentum of the thing is lower than the momentum of the other one. And then it goes back up there. So that is that. What about a plot? of the center of mass of the two systems. Now, in that case, if we think of the system of all the sticks, then the 3 sticks hitting the table have a net external force pushing up on them, so it should have a decrease in a change in momentum. The change momentum should be different than the falling stick. So that's what I want to plot. Well, I'm just going to plot I didn't plot 3 sticks, right? I should make 3 sticks. I'm just going to plot the momentum, and we can see how it compares to. Let's just plot the center mass. Yeah. Okay. Let's just see if we can see that. Okay, so if I go up here, let's make a new variable called center rcom. Okay, and I won't even need to calculate right there. I'm going to calculate it right down here at the end of all this stuff. Rcom. Rcom, the center of mass, is going to be equal to mass 1 times stick 1, no, R1, right? R1 is the center of stick 1. I need to put a parentheses right here. Plus M2 times R2 plus M3 times R3. And all of that divided by M1 plus M2 plus M3. So that's the vector location of the center mass. Now I can plot the y component of that. So it's just going to be rcom.y. That should work. I didn't change the label. I should probably do that. Let's change this to, because someone's going to look at it, y in meters. Okay, so there's the center of mass. Let's see if we can notice anything. No. I mean, it does kind of, it doesn't keep, it maybe straightens out there. Let's do this. Let's do, I got it, up here, before the loop, I'm going to say rcom0 equals m1 times r1 plus m2 times r2 plus m3 times r3 divided by m1 plus m2 plus m3. So this is the center mass before it hits anything, and I'm going to treat that as though it were an object. And I'm going to say rcom p is vector 0, 0, 0. And then rcom m is going to be m1 plus m2 plus m3. So now I can model the motion of this just like I would that other stick. So let's look down here where I changed the stick. Right here. So I'm going to say, what did I call it? rcom0. That was kind of weird. Okay. rcom p. rcom p equals rcom p plus rcom m times g times dt. That updates the momentum. Now I can update the position. rcom0 equals rcom0 plus rcom p times dt divided by rcom m. I think that will work. Now I'm going to plot that. F3 rcom0 dot y. I feel like there's going to be an error here because I kind of did that in a weird way. Okay, I think there's both there. Yeah. So the blue one is the center of mass for the falling ladder, and you'll see that the center of mass is higher than the free falling one. And that's what we'd expect because it has a net force pushing it up. Okay. I'm happy to be done with that. I mean, I like the problem, and it's fun to build things, but I don't like things that get too messy, and that was just too messy for me. And yes, there's a better way to do it. And you should make your own because it's fun. And I just said it wasn't fun. What do I know? Okay, I'll talk to you later.